essentially, if you look at the service mesh capabilities today, we generally talk about identity, we talk about service discovery, routing, as well as policy, but oftentimes what's forgotten about is that there is something that also exists, which is DNS, which is an integral part of service discovery. And it kind of opens up another set of use cases that people kind of need to think about. And that's essentially the premise of our presentation today. I'll talk about use cases while Venil here will go more into how we're looking at it from Kubernetes and Envoy and hopefully Istio as well. So going in a little bit more into how we look at it. So naming in general, if for applications, is fairly complicated in the sense that as you go through your development cycle and applications progress through staging, rather dev, staging, and then towards production, the heart of the application itself remains the same, but the name might change. And as a developer, generally, you don't want to worry about these things. How can you make it kind of simple in terms of deploying an application? So one of the things that we have kind of tried to start to look at it is that can we kind of use DNS to simplify this whole process by simply naming your applications the same, but when you kind of deploy it across multiple clusters or multiple clouds, as long as the name remains the same and you use aliasing or naming conventions which are generic enough for an application, you can kind of simplify the whole process. Taking this also a wider spread towards multi-cluster and multi-clouds, one of the things that also comes up is that I kind of keep bringing up multi-tenant in the sense that you don't generally just have a single user that is accessing the services, whereas also you might have an application or the same application deployed across multiple namespaces within a Kubernetes cluster, not specifically tied to a cluster, but across multiple clusters as well. And then you kind of don't want there to be a name clashing, as well as you don't want services across different namespaces to be able to discover each other. How do you solve that? Today, within the bounds of Kubernetes, there is no way to do that. So that's one of the things that we as a team have been thinking about how to solve. What we were thinking was that you could potentially have a group of namespaces bound together and then combine that and have a DNS kind of servicing that set of namespaces. And in general, by doing that, you're kind of isolating your service discovery to those groups or a single namespace, if you will. And then you potentially cannot have a way of different applications or different services kind of trampling each other, as well as if I am working in the staging environment while someone else is working in a production environment, there's strong isolation in terms of service discovery. Going into more of the use cases, then as a DevOps engineer, when you're deploying an application and kind of looking at it from the view of whether the application is working well, typically we look at telemetry data, but what we look at is HTTP statistics or gRPC stats, but no one kind of thinks about cases where DNS is actually not working. And how do you kind of build some tooling around trying to see whether your application is sluggish because of DNS. A simple example is that sometimes V6 might trample V4 in terms of queries and slow your application down. How do you solve that? So one of the things that we've been thinking about is that can you have something in between your application and a telemetry agent kind of collecting statistics around DNS, measuring request and response times, measuring also who is trying to access that specific service in terms of DNS. Essentially, these are the kind of problems that we've been thinking about and solutions around it. Having collected all that telemetry data, what you can eventually also do is do some behavioral analysis around it, and essentially it opens up the door for security use cases. So this is one of the topics that we kind of have in mind as well. Then, now that we've talked about security, sometimes also as a DevOps engineer, one of the things that you want to look into is that as services are accessing other services within a cluster, you might not want your services to access anything which is outside your organization, and how can you achieve that? So a simplistic example is that I want to deny my front-end service from accessing any of the .com sites as a security measure. Another example would be going back to the tenant isolation case. If you also want to restrict it in terms of policy, you could potentially say that tenant A is not allowed to access tenant B services from a service discovery point of view, rather than once the HTTP request is actually sent out. So within the bounds of this, one of the things that we have been looking at is that can you put a proxy in front of this, doing some kind of layer 7 filtering and achieving these kind of use cases? I'll dive into the last use case, and then I'll give the podium to Venil, who will talk more about the implementation. Now, this is a little more evolutionary, where the IETF and the community have been starting to talk about DTOH, kind of adding some kind of color to it. Essentially, what we were thinking is, now that we have a proxy, can you kind of make your space also private, in the sense that when you think in terms of tenant isolation, you also want to think about privacy, where within the bounds of a tenancy, you should, let's say for some reason, you're able to look at DNS queries. Can you encrypt it and maintain privacy across what you're actually accessing? So this is one of the use cases that we've been kind of thinking that would be useful within the bounds of the topic around DNS. And so here again, essentially the idea was that have a way where during the discovery process, redirecting the traffic through a proxy allows you to do some L7 encryption and forward the DNS query along to any DNS server which might be behind it, CoreDNS or Kube-DNS, if you will. So yeah, with that, I'll have Venil start to talk about some of the implementation details. But before I do, I kind of wanted to bring up the current state of DNS within Kubernetes, where essentially, to summarize, many of these things are not possible with Kube-DNS alone, especially because any kind of configuration to DNS requires you to restart pods or redeploy your deployments. Definitely, there's no policy or any of the evolutionary features. So yeah, with that, I'll give it to Venil.
Thanks, Deepa.
Sure.
Okay, before I dive into the solutions, I want to ask a couple of questions. Who here knows what a service mesh is? There's a lot of hands. Who here really understands what a service mesh is? Exactly. So, but the good thing is there are a lot of learnings that you can take from service mesh. And one of the key learnings that I love about service mesh is the sidecar proxy pattern. And I will be using that pattern to showcase the solutions that we came up with. First, let's look at the Kubernetes DNS as it stands today. We have a couple of services here, A and B. And let's say we want service A to discover service B. And in order to do that, it will send a request to the Kube-DNS or CoreDNS pod in the Kube system namespace. And it will have an IP or a cluster IP. And the request is typically UDP or TCP. And once the response is received from the DNS server, service A can connect to service B using its IP. The first use case I want to go into is the DNS isolation use case. We essentially want to segregate DNS servers for a bunch of namespaces or a selective number of applications. And here is a draft CRD that we came up with. And it's only drafted right now. We want to contribute this to the upstream projects like Istio or Envoy. And what we do here is we select a bunch of namespaces using the namespace selector label. And then we pick all the namespaces having the label env with value staging 1. And for all these namespaces, we want to use the DNS server located at tenant1.dns.svc. So how does this look in real? For example, we have the payment gateway service here, and it wants to access the user's API service. And all of this is a part of the staging 1 deployment. We have a tenant DNS server here, and the Envoy proxy, which is the sidecar proxy for the payment gateway. Here is an open source DNS filter that we used in order to get here. And the payment gateway, when it sends a UDP request or the DNS query, it gets trapped into the DNS filter in the sidecar proxy. And then the DNS filter forwards the UDP DNS query into the DNS server. And once it gets a response, it can connect with the user's API. We can apply a similar policy to another staging environment running in the same Kubernetes cluster. And the services in both of these clusters will not be able to access or even discover the services in other namespaces. The second use case is DNS observability. Here what I have is the CoreOS Prometheus operator, and there is a CRD named Service Monitor, which allows Prometheus to scrape metrics from different endpoints. In Envoy, there is an endpoint named stats/Prometheus, and here we run it on port 8000. And since we have the DNS filter accessing all the DNS queries, we can monitor and we can measure every query, and we can also log queries that are going to external services or internal services. And all of that could be exposed into Prometheus using this operator. We need to specify the application we want to track, and here is the payment gateway application we want to track running in the payments namespace. And in real, it looks like this. So we have the payment gateway and the proxy in front of it, the DNS server for that tenant, and the DNS filter. The payment gateway sends a DNS query to the DNS filter, which forwards it to the tenant as before. But now we generate statistics into the Envoy stats module. And using our operator, Prometheus can scrape these metrics. And then you can integrate Prometheus with third-party solutions like Grafana or some other dashboards. And by observing these kind of metrics, you can make sure that your applications are requesting for the right services, or you can see if there is some malicious requests going out from your system. The next use case is the DNS filtering use case. Here we want to whitelist and blacklist certain domains, and we do that by specifying the policy here. And in the whitelist, we select all the services running in the payments namespace, and we apply this policy on the payments workload, and we want to route all the DNS queries to tenant 1. So specifically, if there is a query that wants to access something outside of the payments namespace, it would be matched here, and probably it would be denied. There is also a blacklist where you can specify a set of domains that you don't want your services to discover. In this case, it's star.foo.com. And if the domain matches this URL, it would fail to even identify the IP address for it. And the last configuration here is the default action. So let's say we haven't listed any domain which the service is trying to access. And in that case, we just want the proxy to log with an error message. We could also specify whether the domain should be allowed or denied even. So in reality, it would look something like this. There is the payment gateway, which wants to access the payment info service. There is the proxy and the DNS server for the tenant. And here is the DNS policy filter. So whenever there is a UDP DNS query, it would be trapped by the DNS policy filter, and it would consult the policies database. And in the previous spec that I showed, we write the policies down in the YAML file itself, but this could also be an external database. And once it decides to accept that DNS query, it can then forward the DNS query to the tenant-specific DNS server. And once the payment gateway receives the response back from the DNS server, it can then connect with the payment info service. But let's say the payment gateway is trying to access a malicious website, for example, api.foo.com. And in that case, the DNS filter can quickly terminate such DNS requests, and the connection will not even happen. But there is a catch here. Let's say the payment gateway is kind of smart, and it already knows the IP address for the external service, which is api.foo.com here. In that case, we can't do anything at the DNS level, but we need to apply some sort of network policies to get rid of such requests. One other thing we can do is we can observe the connections that are initiated. And if there was a DNS query done right before the connection was initiated, then we can allow and probably deny all the requests that originated without any DNS query right before them. Here is an extensible model of the DNS filtering spec. In this case, we route all the DNS policy queries to an external policy server, which understands the gRPC protocol. And whenever a DNS query enters into the proxy, we consult this external service. And by default, we can deny any domains that the policy server doesn't understand. And one other thing we can do here in the spec is we can specify the specific application we want to apply this policy over. And in this case, it's payment gateway in the payments workload. So along with the namespace selector, we also can specify an application selector. The last use case I want to touch upon is the DNS Evolution. Essentially, UDP queries or the DNS queries are plain text. They could be UDP or TCP, but we want to upgrade such protocols to DNS over HTTPS or DNS over TLS, and we can do that very easily with the Envoy proxy. So again, we select the workload payment using the namespace selector, and this time we route such DNS queries to the encryption supporting DNS server here. And we can upgrade the protocol by specifying the protocol field here. And we can specify what kind of protocol we want to use or we want to upgrade to. So in this case, it is DNS over HTTPS. Or it could also be DNS over TLS, for example. So in reality, it would look something like this. There is the payment gateway and the payment info service. We have the proxy like before and the DNS tenant. And in this case, the tenant supports encrypted queries. And whenever the payment gateway makes a UDP request, it gets trapped by the DNS filter. And this time, the DNS filter originates an encrypted connection to the DNS service. DNS over HTTPS is typically done over HTTP2, and that's also good for the network. And once the response is obtained back to from the DNS server in the DNS filter, it can then send a UDP response back to the payment gateway. And once it gets the response, it can connect to the payment info service. That's it. And for the demo, I have a simple application running called the HTTP bin and a sleep pod running via which I'm going to make queries for the HTTP service. I have the same application running as a clone in a different namespace. So the first namespace is acme.com, and the second one is foo.com. We have the tenant-specific DNS services here, and both have their own unique IPs. We also have the Envoy proxy running in front of the sleep service. We don't really need the Envoy proxy in front of the HTTP service for now. And whenever the sleep service in the Acme namespace wants to discover the HTTP bin service in the Acme namespace, it would make a DNS query to the Envoy proxy. The Envoy proxy will then send it to the DNS service. And in this case, we want the HTTP bin service to be discoverable by the sleep service in its own namespace. In the second case, if the sleep pod in the foo namespace makes a query for the HTTP bin service in the foo namespace, we want to allow such requests as well. But if the sleep pod in the Acme namespace makes a query for the HTTP bin service in the foo namespace, we don't want to allow such requests. And the same is true for the other way around. So we don't want the HTTP server running in the Acme namespace even to be discovered by the sleep service in the foo namespace. Let's see that for real. So I have this deployment on Kubernetes, and I have the 3 pods corresponding to each service that I showed earlier. And I'm running the same set of pods in both namespaces. So if you notice, CoreDNS has just one container. The HTTP bin service also has one container, but the sleep pods in both namespaces have 2 containers. One container corresponds to the sleep container, and the other one is the proxy. Now, when I make queries from the sleep services, you will notice the difference. So here I'm making a query, which is a NS lookup query for http bin.acme.com from the sleep container within the Acme namespace. So this should work. And as you see, we received an IP address corresponding to that service. In the second case, we are doing a similar query, but in the foo namespace. So from the foo namespace in the sleep container, we make a query for the HTTP bin service in the same namespace, and we received an IP for that. But in the third case, it fails because the sleep service in Acme cannot access the HTTP bin in foo, and the other way around as well. So sleep service in foo cannot access HTTP bin in Acme. And this is all done by using the DNS filter that I spoke of earlier. And we can do all sort of creative things with the filter. I wanted to show you the code that I used in order to get this working. So we have the DNS policy configuration here for the sleep service. And this time, we are looking at the sleep service for the foo namespace. And for the name server, we drop the Kube-DNS IP address and instead use a localhost IP address. And we don't have any source domains, and we have some other configuration here. And in the same pod, we are running the Envoy container. And this is the Envoy configuration. So if you see right here, we are running the listener on port 53, which is supporting UDP queries. And here is the configuration for the UDP DNS filter. And we list all the domains that we want to track. And here we list both acme.com and foo.com. And if you see here on this line, you'll notice that we route all the http bin.acme.com queries to no cluster, which means that we don't want to have the sleep service discover this particular HTTP bin service. And then the other service running in the foo namespace will be routed to the HTTP bin foo cluster. And that's defined right here, where we also update its name to http bin.foo. The entire FQDN in the Kubernetes namespace. And then we route this query to a CoreDNS server, and that's being set up right here. And in the CoreDNS, for now, we are routing it to the Kube-DNS actually, but we can use a different kind of DNS server instead of CoreDNS and do more contextual queries or more contextual responses. With that, I want to summarize by saying that DNS plays a very important role for service discovery and application migration. And in current enterprise systems, multi-tenancy is extremely important, and it's also very critical at the DNS layer. And as I showed you in the demo, the Envoy proxy can solve some of these interesting challenges with DNS using a filter like the DNS filter. And the best part about Envoy is that you can configure it at runtime by using its XDS APIs. So you don't need to restart the proxy nor any of your services, and everything will work. So if you have new policies that you want to apply at runtime, Envoy will take care of it pretty easily. You can also integrate these DNS filters along with third-party systems to provide richer observability, security, and filtering. So I spoke about Prometheus and Grafana. We could also consider other options here. And finally, I want to mention that we want to contribute this work to the open source and existing projects like Istio and Envoy. And if you have a use case for this work, then please get in touch with us, and we would love to collaborate with you. And if you have any questions, we can speak now, or I will also be available at the booth right after this talk. Thank you.
Or so for questions. Can you hear me?
Yeah.
Anyways, for questions and answers, I will run them around in whatever order I can see them. So, hello.
Hey.
So just curious, how does this differ from using Kubernetes network policies, and when would I want to use Envoy instead of that?
So essentially, Kubernetes network policies doesn't allow you to go into L7 per se. If you want to kind of look at the DNS queries and the responses, and also build some telemetry around it, that's when you'll look at this versus just plain network policies. But having said that, it's useful to even have the guardrails at the network layer, and add this on top.
Gotcha. Thank you.
In regards to making multiple DNS servers everywhere, as in with lots of these proxies, well, like what type of impact would you be looking at? Obviously, you're putting down lots more core DNS pods, you're putting all of these filters down. How much of an impact are you talking about? If you've got a really large cluster, you're going to have a lot of containers that are running.
So the boundary around that is a group of namespaces. So it just depends upon how many namespaces you want to have the DNS serving. So the dimension is not at the level of the services or the pods, but it's more at a higher level. So it just depends upon how many namespaces you would have on that cluster, or across clusters as well.
Yeah, I haven't tried it looking at even at deployment level, going beyond namespaces, going even deeper down.
I'm sorry, I didn't hear the last
Did
part.
you think about going into deployments, going deeper down, not just namespace level, but deeper into actual deployments having their own DNS service?
That could be an option, but then scale would be a challenge there. Yeah.
So my question also was similar to the network policy. So that is one. Second thing is, like, Istio also provides RBAC, right? So that can also do a denial of service for the service levels. So you can restrict like which service can call which service. We can put various filters there itself, right?
Yeah, but you can't do it at the DNS layer today, and this is what we want to bring into Istio as well. You can do it. You can put L7 policies on HTTP and gRPC requests, but not at the service discovery layer in terms of DNS. So this would be an add-on, and we likely leverage RBAC, but yeah.
No, my question is, like, it provides the same experience only, right? I mean does it add any more value to that?
So let's say you are running some secure applications like in a single cluster, and you don't even want the other like tenant to to discover these applications or even the IP address. So this is just adding an extra level of security in that sense.
Yeah, so it kind of ties in well. It adds a layer on top again, as I said for L4.
Okay. Couple more up front.
That's a question.
So kind of adding to what he was saying, so with Istio, when you have like service entries or you have the registry only mode, you kind of can do this kind of DNS filtering because you're limited to the namespace or whatever you're trying to expose to your Envoy proxy. So why is this sort of, I mean, this would be including like a new CRD or something like that, but why isn't it something that we can expand using the registry only mode, for example?
I'm not sure of the registry only mode.
You're talking about specifically in terms of isolating DNS?
So it kind of boils down to DNS in a sense because what you can do with Istio when you have the registry only mode is that all the outgoing requests are limited to whatever you've actually whitelisted for your particular workload. So whatever is visible to it within the namespace or visible to it within like another namespace for a particular application. So it's already kind of restricted. And so anything that you're trying to resolve, if Envoy doesn't already know about it, it's not going to be able to route the request anyway.
Yeah. So this solution is not specific to Istio. I mean, you can take this and run it on like just Envoys or you don't even need a service mesh per se. This is like a generic solution, but you can adopt this in different ways. I mean, these problems can also be solved in Kubernetes or in CoreDNS. So this is one way that you can approach.
Yeah, and service entries is also complicated in terms of even scale. If it bring in the dimension of scale, it's fairly complicated. This is a lot more simpler and actually solves the problem at the heart, which is add the DNS layer rather than add something on top to solve it. So we're kind of trying to go ground up. We've been playing around with service entries quite a bit within the bounds of service mesh and kind of trying to see, okay, if you had to rethink it, and see if there's a different way where essentially, okay, DNS isolation is a piece, take it even cross-cluster, but then with this, you can also think about more use cases, right? Like we brought up telemetry and observability, which is kind of not something you can do with the current Istio code base right now. So, go ahead.
Thank you for the presentation. I was thinking of, currently there is the node local DNS cache that is currently in beta, right? And I was thinking exactly what you're doing is kind of these like decentralization of DNS, but not at node level, and rather at like namespace level. But in node local DNS, there is a caveat that you lose high availability if your DNS is not ready, if your DNS server is not ready. So how would you like solve this issue with having this single point of failure in each namespace for the local namespace resolution?
So are you saying that the DNS server for the tenant is not ready? And yes. I mean, I think that's like a bootstrap problem, which is it's a general problem, I think, with any of the DNS solutions we have right now. One way, I mean, with the filter, you can do something like you can keep querying for the uptime of the DNS server, and then you can probably start responding. So, and that could be a part of the health check of the proxy itself. So you can play around like that.
Yeah.
All right, I think that puts us right at time. So if you have any further questions or conversations, hallways are great places for that. I think it's lunchtime now, actually, so enjoy. Thanks, everybody.
Thank you so much.
And thank you so much for Deepa and Venil.
Sure.